A structural causal model is not merely a directed graph decorated with probabilities. It is a system of assignments equipped with intervention semantics, a rule for generating endogenous variables from background conditions, and a rule for constructing new systems when mechanisms are replaced. From that object, we can derive observational distributions, interventional distributions, and counterfactual variables. But every derivation depends on exact conditions, domains, solvability, independence, invariance, and identification. This film develops that object formally, from its signature to the limits of what lower-level data can recover. Begin with a signature. There is a set U of exogenous variables, a set V of endogenous variables, and a range for every variable. The structural model adds a family F containing one assignment for each endogenous variable. A probabilistic SCM also supplies a probability measure P of U. A deterministic model may instead be evaluated at a fixed context U. Our running system has 4 endogenous variables. Z precedes X and Y, X precedes a mediator M, and Y responds to X, M, and Z. The notation on screen specifies the domains and the 4 structural maps. Nothing causal has yet been estimated. The model is a proposed data-generating system. For each endogenous variable V sub I, its structural map takes selected endogenous parents and selected exogenous inputs into the range of V sub I. We write : to mark assignment. The parent set is not defined by correlation, it is defined by functional dependence in the structural map. If changing one argument while holding the others fixed can change the output, that argument is a direct cause relative to this model. Algebraic invertibility does not reverse that claim. Solving X from an equation for Y may recover a value, but it does not construct the submodel produced by intervening on X. Causal direction is carried by the assignment family and its replacement semantics. The exogenous variables encode variation not explained inside the model. General SCMs permit shared or statistically dependent exogenous variables. Independence is an additional restriction, not part of the basic definition. Once a complete context U is fixed, all structural maps are deterministic, but determinism alone does not guarantee a unique endogenous state. A context determines a unique world only when the structural equations are uniquely solvable. When a probability measure is placed on U and a unique solution map exists, pushing that measure through the solution map induces a probability distribution on V. Randomness therefore belongs to the distribution over contexts. Causal structure belongs to the assignments. In a recursive SCM, the induced directed graph is acyclic. Its vertices admit a topological order, and the solution is obtained by substitution along that order. In the running system, evaluate Z from its exogenous input, then X from Z, then M from X, and finally Y from X, M, and Z. Every structural map is evaluated exactly once after its endogenous parents are known. This proves existence and uniqueness of the solution for every context. It also defines a measurable solution map from U into V under the usual measurability conditions. Recursiveness is thus a powerful sufficient condition for well-defined observational, interventional, and counterfactual distributions. A cyclic SCM has no topological solution order. Its assignments must instead be solved simultaneously. Existence, uniqueness, and measurable dependence on the context become separate requirements, and they must be reconsidered after interventions and marginalization. A fixed point can be unique, multiple, or absent. Worse, an observationally solvable cyclic model need not remain uniquely solvable after one mechanism is replaced. Modern treatments therefore distinguish observational solvability with respect to subsets of variables, and classes, such as simple SCMs that preserve useful properties under intervention and marginalization. From this point onward, we restrict the derivations to acyclic models and mark every result that depends on that restriction. The induced graph is a projection of the structural maps. Draw an arrow from V sub j to V sub I exactly when V sub j is a functional parent of V sub I. For the running system, the directed edges are z to x, z to y, x to m, x to y, and m to y. The graph retains parenthood and discards the functional forms, variable ranges, exogenous coupling, and solution values. A missing edge is therefore an exclusion restriction. The omitted variable does not enter that assignment directly. Two distinct assignment families can induce the same graph while implying different effects, different counterfactuals, and even different observational distributions. Now impose acyclicity and mutually independent exogenous components associated with the endogenous assignments. This is the Markovian case. The induced observational distribution obeys the causal Markov factorization. The joint density or mass function is the product, over endogenous variables, of each variable conditional on its graphical parents. In the specimen, this becomes P of z times P of x given z times P of m given x times P of y given x, m, and z. The factorization follows from the structural construction and exogenous independence. It is not a definition of causality, and the same observational factorization may be compatible with several Markov equivalent directed acyclic graphs. If z is unobserved and marginalized, its common influence on x and y is represented in the latent projection by a bidirected edge between x and y. The observed graph is then an acyclic directed mixed graph. Directed edges encode observed ancestral causal routes that survive projection. Bidirected edges encode latent common cause routes. In the semi-Markovian representation, independent exogenous variables may each be parents of at most two observed variables, which is sufficient to represent the bidirected structure. The relevant graphical units are now districts, maximal sets connected by bidirected paths. District structure, not ordinary parenthood alone, controls the decomposition used by general identification algorithms. Separation must also change with the graph class. In a directed acyclic graph, deseparation blocks paths according to collider and non-collider rules. In an acyclic directed mixed graph, the corresponding criterion is M-separation, which treats arrowheads from directed and bidirected edges uniformly along a path. The global Markov property converts graphical separation into conditional independence. Causal minimality adds that no directed edge can be removed while preserving the Markov property. Faithfulness adds the converse direction. Every independence in the distribution is explained by graphical separation rather than parameter cancellation. Markov, minimality, and faithfulness are different assumptions. Only the first is entailed by a Markovian SCM. Independence in a Markovian model has a local boundary. The local Markov property states that each variable is independent of its non-descendants once its own parents are given, strengthening that to independence from every remaining variable identifies the Markov blanket. For any variable, the blanket is the union of its parents, its children, and the other parents of those children. It always shields the variable, and under faithfulness, it is the minimal such set. Conditioned on its blanket, the variable is independent of the entire rest of the system, and nothing outside the blanket carries additional information about it. A Markov chain is the simplest case, in which each variable is shielded by its immediate predecessor and successor alone. The blanket therefore marks the exact locality of a mechanism. the smallest set a sufficient predictor of the variable then requires, and the point at which the remaining graph becomes irrelevant. The observational layer contains distributions generated without replacing any mechanism. It can test conditional independence implications, but it generally identifies only an equivalence class of causal structures. In the fully observed acyclic case, two directed graphs are Markov equivalent exactly when they have the same skeleton and the same unshielded colliders. Their shared observational independences can be represented by a completed partially directed acyclic graph. With latent variables, partial ancestral graphs play the analogous role for equivalence classes containing directed and bidirected uncertainty. These representations state which edge marks are compelled and which remain unresolved by the assumed independence information. Intervention requires an invariance postulate. Relative to a declared family of interventions, replacing selected assignments is assumed to leave every unselected assignment and the exogenous law unchanged. This is modularity. It is not guaranteed by the : symbol, and it is not a universal fact about the physical system. It is part of the causal model and must be defended for the interventions under study. If setting X also changes the mechanism for Y through an unmodeled route, then the proposed submodel is wrong even if the observational equations fit perfectly. Intervention semantics therefore consist of both a replacement rule and an explicit claim about what remains invariant. A perfect intervention due of X equals X replaces the assignment for X by the constant X. The resulting submodel, conventionally written M sub X, retains the remaining assignments and the exogenous distribution. Graphically, all arrows entering X are deleted. Multiple variable interventions replace several assignments simultaneously. A soft intervention replaces the mechanism for X by another function while possibly retaining some parents. A stochastic intervention replaces it by a random kernel, and a policy intervention may condition that kernel on variables observed before the decision. Each case is mathematically distinct. An intervention is fully specified only when the replacement mechanism, its information set, and the invariant remainder are all stated. In a fully observed Markovian acyclic SCM, perfect interventions are obtained by truncated factorization. Delete the conditional factor belonging to every intervened variable and substitute the assigned values into the remaining factors. For do of X equals X in the running graph, the post-intervention law factorizes as P of Z, P of M given X, and P of Y given X, M, and Z. Summing out Z and M yields P of Y under do X. In the linear specialization, M : equals Bx plus U sub M, and Y : equals Cx plus Dm plus Ez plus U sub Y. The total causal slope from X to Y is C plus Bd, one direct path and one mediated path. A counterfactual variable is defined by solving a submodel out of context. Y sub X of U is the value of Y in M sub X when the exogenous variables equal U. For evidence E equals E, abduction forms the posterior P of U given E. Action constructs the submodel. Prediction pushes that posterior through the submodel solution map. The result is a distribution such as P of Y sub X given E, not necessarily a single value. In the linear specimen, holding U fixed preserves Z and all disturbance terms while X is replaced. The difference Y sub X of U minus Y sub X prime of U equals the total structural coefficient times X minus X prime. Recursive SCM counterfactuals satisfy structural consistency laws. Effectiveness gives X sub X of U equals X. Composition says that forcing a variable to the value it would already attain does not change the remaining solution. Consistency identifies the observed outcome with the potential outcome under the treatment actually received. Reversibility supplies another constraint on recursive systems. These properties restrict which joint counterfactual distributions can be represented by an SCM, but they do not identify those distributions from observational data. Identification must quantify over all models compatible with the graph, functional restrictions, and available distributions. Counterfactuals require a coupling across submodels. Two SCMs can agree on P of V and on every single-world interventional distribution while disagreeing about the joint law of y sub x and y sub x prime. The disagreement lies in how the same exogenous variables are shared across worlds. A twin network makes that coupling explicit by duplicating endogenous variables while sharing their exogenous ancestors. A single-world intervention graph instead splits treatment nodes to encode the counterfactual variables and independences associated with one intervention regime. Neither representation creates identification. Each exposes which cross-world or single-world assumptions a proposed derivation uses. The causal hierarchy orders three families of distributions: observational, interventional, and counterfactual. A fully specified SCM entails all three. Lower layers generally do not determine higher ones. The causal hierarchy theorem formalizes this generic non-collapse under stated model space and measure conditions, models in which lower-level information uniquely determines a higher-layer form an exceptional set of measure zero. This is not an absolute impossibility theorem. Randomization, functional restrictions, monotonicity, invariance across environments, or additional experimental distributions can identify particular higher-level targets. The conclusion is conditional. Every bridge between layers must be supplied as an assumption or a source of information. Identification asks whether a target has one value in every SCM compatible with the available distributions and causal assumptions. In latent variable acyclic graphs, the ID algorithm first restricts to relevant ancestors, augments the intervention set when allowed, and decomposes the remaining graph into districts. Recursive district factorization either returns an observed data functional or reaches a graphical obstruction. A hedge provides a witness of non-identification by supporting two compatible models with different causal effects. Failure of point identification does not end the analysis. Structural restrictions may yield sharp bounds, as in non-parametric instrumental variable models. Counterfactual targets require parallel world or counterfactual graph algorithms and can fail even when all single-world effects are identified. Identification is distinct from estimation and from discovery. Identification is a property of a causal model class and an information set. Estimation concerns recovering the identified functional from finite samples and additionally requires positivity, regularity, and control of statistical error. Discovery attempts to restrict the graph or functions from data and is conditional on assumptions such as faithfulness, non-Gaussianity, additive noise, equal error variances, temporal order, or interventions. Transportability is another identification problem. Selection diagrams mark mechanisms that may differ across populations, and transport formulas determine whether source experiments and target observations can be combined. None of these procedures removes assumptions. Each makes a different set of assumptions operational. The structural causal model is now fully specified as a formal system for causal reasoning, a signature, structural maps, a context or exogenous law, solution semantics, and an intervention family with declared invariances. Its graph is a lossy projection. Its observational law is one consequence. Its interventional laws belong to replace submodels. Its counterfactual laws couple those submodels through shared exogenous variables. Separation, equivalence, district factorization, hedges, bounds, and transport formulas describe what can be recovered when the full model is not known. The discipline is exact. Define the variables, state the assignments, prove solvability, specify the intervention and separate entailment, identification, estimation, and discovery. Neural cipher. Deciphering learned computation.